All right, so any questions before we jump into this? Yes? Post the what? PA3, I can show you PA3. I can post you an executable that you can run. I don't want to give sample output because then somebody will mimic the sample output exactly and it will only do that. But I can show you now, or I can post an executable if you want to be able to run it yourself and see what it does. Would that work for people? But let me do both. Although I have to find it if I'm going to do that, so let me see if I can find it quickly. All right, so PA3 use message. Show me the stack's empty. Show me the queue is empty. Let's go into stack mode. Let's insert a 10, look at my stack, insert a 20, look at my stack, insert a 30, and a 40, and a 50, look at my stack. Okay, top of the stack on the left, output in a single line. Let's switch to queue mode. Input a 10, there's my queue. Input a 20, there's my queue. Input a 30, there's my queue. Input a 40 and a 50, there's my queue. Okay, head of the queue on the left. So let's go back to stack mode. Let's do a pop, and the 50 comes off, and my stack looks like that. Do another pop, and the 40 comes off, and my stack looks like that. Go into the queue and do a remove, which is also a P for some reason. And it removes the 10, and there's my queue. Remove the 20, there's my queue, and so on. So I can keep removing from my queue until my queue is empty. If I try to remove one more, it gives me an error saying the queue is empty. If I go back to my stack, it still had those things on it. Yes?
So just to confirm, for the P command, you print the item that was removed and
yes.
not the thing itself?
Yeah, you print the thing that was removed.
Okay, that's a little confusing.
Okay. Yeah, P just shows you the thing that's removed. The only time that you print the stack or the queue is when you say stack or queue. So you can remove the 30 and the 20 and the 10, and then the stack's empty. And I think that's pretty much all it does. Yeah?
And for the size, just we can define whatever we want.
What size of what?
Size of the queue.
Where would you, suppose I said the size is 100, what would you do with that? Okay, because you're implementing this with a list. You're not using an array, so there's no inherent size. Okay.
Wait, so the list, it can only hold like data and next points, right? But the central node can be any type of node, right?
Yeah, you can add a tail pointer to it to keep track of the end of the list, but you got to do something with the queue so that you can get directly to the end of the list.
Yeah, but the rest of the node, like all the data that you input, it has to be like a node where it only.
It'll still have a tail pointer. That's okay.
Oh, it can?
Yeah. For the queue, your node can have data and 2 pointers.
Okay.
But don't set it up as a doubly linked list, right? Set it up with the sentinel's tail pointer pointing to the last node in the list. Yeah?
Are you okay with inputting the same number twice?
Sure. Yeah, it's a stack, so, right, we can do this, and there's your stack. And there's no notion of sorting or anything like that, okay? It's a list, but it's not a sorted list. So it's a list that's being used to implement a queue and another list to implement a stack. So other questions? And no memory leaks. Okay, so free all the memory from your stack and your queue. Free when you pop or remove, and free everything when you're done. All right, other questions? So we had been talking about binary search trees, and I'll draw my favorite binary search tree. It's not really my favorite, but I like it. So that's a BST. So remember, what does it mean to be a BST? It means that for any node, everything on the left is less than that node, everything on the right is greater than that node. Okay, so if we look at the root 40, everything over here is less than 40, everything over here is greater than 40. Okay, if we come down here and we just look at this tree rooted at 60, everything on the left is smaller, everything on the right is greater. That's what makes it a search tree. And it's binary because we got 2 or fewer children coming off each node. So the first question is, how can we traverse this tree? So traversing a data structure is a general concept. Traversing means, and I'm going to say visiting each node. So we want an algorithm that allows us to start from the root and somehow visit each node in this tree. And what do we mean by visit? Well, typically we'll mean print the value of the data in that node. But more generally, it just means somehow encounter each node in this structure. Now, in a linked list, traversal is really simple. You start at the sentinel, you see what that points to. That's visiting the first element in the list. That has a pointer to the second element, so if you follow that pointer to the second element, now you've visited the second element. And if you keep doing that until you get to a node whose pointer is null, you know you've visited every element in the list. So traversal of a linked list is very, very simple. Traversal of an array is even simpler. You just use a for loop for I equals 0 to whatever the last index is, and you can access element I. But for a binary tree, it's not so clear how to do this visitation. So we can certainly start at the root, because that's what we actually have access to. But from here, we have a choice to make. We could come over to the left and visit the 20, or we could come to the right and visit the 60. And whichever one we do, we've got to somehow remember that there's another thing we have to do later. So let's say we're going to start off by going to the left. So we're going to come down here and visit the 20, but before we do that, we've got to somehow make a note that we need to come back here and visit the 60. So I'll just put a little note over here, and I'll call this to do, and say, don't forget to go and visit the 60. So I'll visit the 20, but once I've visited this node, I have a choice. I can go to the left or I can go to the right. So I'll go down to the left, but before I do that, I'll make a note which says I also need to come back and visit 30. So I'll come down and visit 10, and now that doesn't lead anywhere. So there's nothing to the left or the right. So I can either go back to the 60 or I can go back to the 30. Let's just go back to the 30 for now. So I'll take that off my to-do list. I'll visit 30. And then there's nothing to follow on the left or the right of that. So I'll go back to my to-do list, and I'll say, oh yeah, I had to visit 60 also. So I'll go up here to 60. And now I have to visit the left and right nodes. So maybe I'll choose to visit the left, but I need to remember to come back and visit 70. So I'll go to the left and do 50. There's no children there. I'll come to my to-do list, visit 70. There's no children there. There's nothing left on my to-do list. I know I visited every node. So that's an example of traversal. But it requires us to sort of keep this list of things that we have to do. And this list will grow the bigger the tree is. If this tree has 10 levels to it, by the time we get down to the bottom, there's going to be a whole bunch of nodes that we need to come back and revisit later. So we'd like an algorithm for doing this traversal systematically. So I'll give you 4 algorithms. 3 of them are very much the same. The first one is what's called LNR, and this is also called in order traversal. And here's the intuition for LNR. Start at the root and move as far to the left as possible. Go left, go left, go left until you have a node that has nothing on the left anymore. Okay? Visit that node, print out its data value or do whatever. So we'll start at the root, we'll come all the way down to the left until we get to a 10. We can't go any further left. Let's visit that. So we'll print out its value, which is 10. That's the L part, right? Then go to the node that led you to that 10, right? So we got down to a 20, we went to the left, and we visited 10. So now visit the node that we came from, which is a 20. So let's print out that value. And now go to the right and do this all again. So we'll go to the right, and if there was anything to the left, we'd come all the way to the left. And we'd visit that node, and then we'd go to its parent, and then we'd go to the right and repeat. Well, in this case, there's nothing else on the left, so we'll just visit 30. All right, well, how did we get to this 20? Right, we followed it to the left of this node 40, so that's the node. So visit the 40. And then go to the right and do this all again. So we come down here to this tree, but we don't visit 60 left. We have to go all the way to the left. So we go to the left, and that brings us to 50. And then we visit the node, and then we go to the right. Now that's confusing. Okay, that's kind of awkward. But if we do this left node right traversal, what we end up doing is visiting our nodes in increasing order, assuming it's a binary search tree. Okay, we'll get our data out in order. So it comes out like this. All right, there's a similar called left-right node, and this is also called post order. Same idea, but the first thing we do is go all the way to the left, and then if we can't go to the left anymore, we go all the way to the right, and then we visit a node. And this is going to visit the nodes in this tree as follows. We're going to go left, left. We're going to visit the 10. We can't go to the left anymore, so we'll pop up to the 20. But before we visit that, we'll go to the right, which will bring us to the 30. And then we'll visit the node, which is a 20. And then we'll pop up here. We already traveled all the way down the left. Before we visit the 40, we're going to travel down to the right. And we're going to traverse this tree using left-right node. So start at the 60, go to the left gives us 50, pop up and go to the right is 70, visit the actual node is 60. Now we've traversed this and we've traversed this. Now we can visit the node, which is 40. There's also node left, right, which is pre-order, which says visit the node first, then go to the left, then go to the right. So the first thing we'll visit is the root of the tree, which is 40. And then we come down to this subtree, and the first thing we visit is the root of that tree. And then we go down to the left, and we visit that node. We go to the left and right, there's nothing there. Now we come back to the 20, we visited the node, we visited the left, let's visit the right. So there's a 30, visit the node, nothing to the left or the right. Now we come all the way back to the 40. We visited the node, we visited the left, now we have to visit what's on the right. And same thing, first we visit the 60, then we go to the left is 50, and then we go to the right is 70. Okay, here's what's weird about all of these things. We need lots of fingers. right? We need to say, okay, we're starting with the 40. We're going to visit down to the left now, but when we're done, we've got to come back to the right. So we need to somehow remember that we got to get to the 60. So we visit the 20, and then we're going to have to go to the left, but eventually we're going to have to come back and go to the right. So we need another finger here, right? And as we go down the tree, we need to remember all these places we need to go back to and visit. Now you can do this, but you need to create something like a stack, right? Because the last place that I put my finger, right, I came to the 20 and I was going to the left, but I need to come back and go to the right. That's the next thing that I need to go back to. I'm going to visit the right of this before I come all the way back up here and visit the right of the 40. So we're using a stack-like structure here. But this is kind of a pain to code, and we're not going to do that. Let me show you one other search order, which is breadth first traversal. This is the easiest one for people, because breadth first says basically start by visiting the root, and then go down one level and just pick up everything that's at that level. So the 20 and the 60. And then go down another level and pick up everything that's at that level. So the 10, the 30, the 50, and the 70. And if there was a fourth level to the tree, we just pick up everything on there. So we're visiting like this. All right, so there's a better way to do these traversals. But I'm not going to tell you yet. All right, there's a big, horrifying binary search tree, unless I messed up somewhere. So let's not traverse this, but let's look at searching. So suppose we want to search for the number 55. All right, start by looking at the root. And we can ask, is this equal to 55? And it's not. Because it's a binary search tree and because 55 is bigger than the root, which side of the tree is 55 going to be in? It's got to be in the right side, right? So we throw away the left side of the tree, and now we just have to search this smaller tree for 55. 55 is smaller than 60, so it cannot be to the right of 60. It's got to be to the left. So now we just have to search this very small tree containing a single node. And the root's not equal to 55. If 55 is in this tree, it's got to be to the right, but to the right we find a null. We know 55 is not in our original tree. Now if we search for 63, same thing happens. It's bigger than 40, so we search here. It's bigger than 60, so it's got to be in here. It's smaller than 65, so it's got to be in here. We compare it to the root. It's equal to 63. It's in our original tree. And this is playing high-low. This is roughly cutting in half the number of nodes that we need to check. Right? The size of the space within which our number might be contained is roughly getting cut in half each operation that we do. Okay, so this is going to be a log n operation in general. So search is very efficient. And it's going to turn out insert is also very efficient. Because if I wanted to insert a 55, pretend we're searching for it, start at the root, come down here, come down here. It should be to the right of 50, but there's nothing to the right of 50. That's where you put your new number. Go to the right, add your 55. And it's guaranteed this is still a binary search tree, because we got here by making sure that we followed that property of a BST, that everything to the right is bigger than the root, everything to the left is smaller.
So what if you try to insert another 55?
So forget about dupes. We're just going to say you're not allowed to have dupes in this tree. So search before you insert. So searching is pretty straightforward. Inserting is pretty straightforward. Traversing is kind of ugly. But how do we do this, right? So you have some temp that's equal to your root. You compare your data that you're inserting to or searching for to your temp data. If it's bigger than that, then you set temp equal to temp right, and you go back to the top of your loop. And you keep doing this until you either find your number or you find that temp is null, in which case it's not found.
I guess it's a little off topic. What would happen if you were to delete 40?
Deleting is a whole different story. So we'll come back to deleting, but it turns out if we were to delete 40, the easiest thing to do is, yeah, so you take either the largest thing from the left or the smallest thing from the right, and you move them up. So we could put our 50 up here, and that'll orphan the 55, but it can get adopted by 60. So that would be our new tree. But there's a two-step algorithm. We'll go through that.
Can you just like hook up 20 to 60? Is that not as easy?
60 already had something on the left and the right,
And so does 20.
right? And so, yeah, theoretically, we could just take the 20 and hang it off there, but
I guess if you were to do that, 39.
yeah, you could put 60 over 39. But that only works if you got that, right? And in general, you may not. But the algorithmic way to do it is to basically replace the root with either the largest thing on the left or the smallest thing on the right. That preserves the search order, and the largest thing on, well, the smallest thing on the right, for example, is not going to have a left child, because that would have been smaller still. So we move that to the root, and if it had something to the right, the parent will be able to adopt it. That's a whole algorithm we'll have to go through when we get to deletion, but we're not quite there yet. All right, so let's look at implementation. I'm not doing PDFs on these, by the way, because I think that's part of what's crashing the software. So you can speed through the video file and make screenshots or something. So let's look at implementation. So what does our node look like? It's got a piece of data. We'll stick with integers, but it could be anything that we can compare. And it's got a pair of pointers. So left and right are struct node stars. So our node is kind of like a linked list node, but it's got an extra pointer. So there's a piece of data, and then there's a pair of pointers, one to the left child and one to the right child. And those can be null if there's no child. We don't need a parent. And you can make trees where you also keep track of your parents, kind of like a doubly linked list. It can clean up some of your code. But let's stick with just pointing down the tree for now. But yeah, that's a definite option. All right, so that's our struct node. And we're not going to have a sentinel. Okay, so when we have the root of a tree, it's going to be a struct node, and it's going to be the address of the root. And if our tree is empty, then that root is going to be just null. Okay, so no sentinels when we're doing trees. That's going to be really important. So we could say struct node root. So I'll post a node EP tomorrow morning and have you start playing with this structure. So you'll be creating a tree manually with a couple of nodes in it, 3 nodes. And then we'll do some manipulations Thursday and Friday. So root will be a struct node, and originally it's going to be null. That means that your tree is empty. So let's actually go ahead and initialize that. And then at some point we're going to add things to this tree, and somewhere along the way we're going to have a tree where root's actually pointing to the root node, and it's pointing to some children, and so on and so forth. Okay, so let's think about how we can traverse. So this will be a void routine. And we want to do in order traversal, so left and then node and then right. Well, the whole way this is set up, if we think about what left node right really means, start at the root of the tree. All we have to do is traverse this subtree in left node right order. And then print out the 40, and then traverse the right subtree in left node right order. And that'll traverse the entire tree left node right. Well, how do we traverse this in left node right? Traverse the left subtree left node right, then print out the root, then traverse the right subtree left node right. How do we traverse this single node tree left node right? Well, we're just going to print out the 10, right, the root node value. But technically, we're traversing its left subtree, which is null, which doesn't print anything. Then we're printing the 10. Then we're traversing its right subtree, which is also null and doesn't print anything. So think CSE 215 induction. And that's just about all you need. So how do we traverse the tree whose root is root? Traverse root arrow left, print out root arrow data, traverse root arrow right. Is that legal?
As long as root arrow left and root arrow right are not null.
As long as they're not null. There's a problem with this the way it's written. When I say traverse root arrow left, the first thing that's going to do is traverse that root's left, and the first thing that's going to do is traverse that root's left, and it's going to do this forever. Although in reality, if it didn't do it forever and root was null, I would blow up when I tried to access root data, or eventually root's going to be null and root left will blow up. So we need a base case here. We need a way to get out of this rabbit hole that we keep going down. So what's the base case here? If root equals null, return. And with that, this should work perfectly. But that may look kind of quirky because it doesn't seem like we're doing anything. We've got one print statement, which is just printing the data at the root. That's the only thing that we're actually printing. But somehow this will do all of that descending down and going to the left and coming back and printing the root and going down to the right and to the left and so on, and keeping track of where we were, all those fingers on our tree that remember where we should go back to when we finish traversing a subtree. All that happens in these 4 lines of code. So this is classic recursion. Okay, it looks like we're not actually doing any work. And in some sense, we're not. right? Each time we call traverse, we're handing our subproblem to a friend, but it's a subproblem. We're asked to traverse the entire tree. We make a smaller problem, which is traverse this subtree on the left. And we hand that to a friend and say, go ahead and print out all the nodes in this. And then we print out the root data, and then we take the subtree on the right and hand that to somebody else and say, go ahead and print out all those nodes. And then we're done. Right? And the trick is our friend is actually ourself. What? Yeah, yeah. First rule is don't talk about it. So, yeah, so this is a classic recursion. Okay. And when you're comfortable with thinking about things this way, things get really, really easy, right? Writing a traversal that uses a while loop and keeps track of where you are using a stack and such is fairly cumbersome. It's straightforward, but it's pretty cumbersome, right? There's a lot of things to take care of. This does the same thing. It uses the computer stack, so that's where all this stuff is being saved, is that every time we call traverse, the current value of root is being saved on the stack. It's a local variable, right, because it's an argument. So when we call traverse, we get a new instance of traverse within which root is equal to the left child of the previous root. But that previous root is still saved. It's sitting on the stack. And when we finally return either here or here, that previous value of root will be restored from the stack. It'll pop. And we'll continue executing using that old value of root. So that's where the housekeeping is happening for us. The OS, in some sense, is taking care of it for us, because when we say call, it gets pushed into stack. And when we say return, it pops off. But this is logically how we eventually start to think about operations like traversal. Traverse the left, print the root, traverse the right. And this will only work, right? This will only work if we know that these will work. But it's not really circular, because these are working on a smaller tree than what this is. The left child is going to have a smaller height than the height of the original tree because it's missing the root. And the right child will have a smaller height than the original tree. So these are smaller problems. And if each time we call this, we get a smaller problem, eventually our problem will get so small that the root will be null. And if the root is null, we know that this does exactly the right thing, which is don't print anything, don't blow up, just return. So buried inside here is a nice mathematical induction proof that this algorithm works. And we could make a proposition P of n, where n is the height of a tree, that this algorithm will successfully traverse a tree of height n. And we know that it's true for the case where the tree is empty, which is actually height of -1, because if the tree is empty, it doesn't print anything. And now you just have to believe if it works on a tree of height n-1, it'll work on a tree of height n. And that's saying if we believe that these work, then we believe this whole thing works. And it clearly does, because this gives everything on the left, this is the root, this is everything on the right. So it's really all tied into induction, but it's recursion in this context. All right, so traversal is very straightforward once you make peace with recursion. Let's look at insert. So we're going to pass it a struct node pointer, which is the root. And what are we going to do? Well, we can start at the root. We can see if we're bigger or smaller than that, and we can move down and see if we're bigger or smaller than that, and move down and continue until we get to a point where we say we should move to the left or the right, but there's nothing there. And then we can go ahead and add that. But how can we think about inserting into this tree recursively? Is there a way to describe inserting into this tree in terms of inserting into smaller trees?
You can write that search function.
Yeah, you want to start with the search. Well, in the case where we don't have to.
Well, let's do search. That's a good idea. So let's do search first.
The search is going to be, search is basically a traverse. You just see if you find it. So instead of printing it, you will just say, hey, I found it.
Okay. But we don't really need to traverse the entire tree to search.
Right.
We really just need to find it. Okay, so if greater than left, or right if less than left. So if we're searching for a 55, we can look at the root and say, let's go to the right. We can look at that, go to the left. There it is. If we're searching for 56, we go to the right, we go to the left. We try to go to the right. There's nothing there. It's not in the tree. But let's not loop. We can do that with a while loop. Let's try to do it with a recursive call. So suppose you're searching for some number n in this entire tree.
What you would do is you would start with an if statement.
Okay.
N is equal to root arrow data.
Mm-hmm.
And
Then it's found.
if it's found, then you just return a 1.
Right.
Then if it's not, then you would check is n greater than. If n is greater than, then you search in root arrow right,
Okay, perfect.
left.
So if the number we're searching for is not equal to the root and is bigger than the root, we don't have to do anything with the left side of the tree. All we have to do is know if our number is in this right side of the tree. Now, how do we do that? Let's use our search function. Right? Forget looping. Let's just call search. So if, and we got to have something we're searching for. So we'll search for number. If num is equal to root data, then it's found. If num is bigger than root data, then let's search the right subtree for our number. And if our number is found in that right subtree, then it's in the original tree. Yeah, and if it's not in the right subtree, it's not in the original tree because it could only be in the right subtree. So we can just return whatever this call to search returns. And if num is less than root data, search the left. But we got to do a base case. You're almost always going to need some kind of base case. Because again, if I'm searching for a number that's not in the tree, if it's bigger than, let's say, every number in the tree, this is going to be true. I'm going to search the right subtree. It'll be bigger than the root of that subtree. I'll search the right subtree. This is just going to keep going down further and further and further to the right. And eventually, it's going to get to a point where root arrow right is null. And as soon as I do that and I try to look at root arrow data, I'm going to segfault. So we've got to have a base case. And our base case here can simply be if root is null, then return not found.
That would work if you have an empty tree.
And that'll also work if your initial root is empty. And this is the only place that we actually say not found is when your root is null, which is a little weird. But that was another clue that we needed a base case because there's nothing in here that ever returned not found. Right? So the only time it returns not found is if we're searching an empty tree. But if we're searching a big tree for something that's not found, remember we keep subdividing the problem. Eventually we're going to get down to a case where the root of our tree is null, there's where our base case fires. Say what? Yeah, it'll help with the insert actually. You could, but we're going to be lazier than that. So this is technically one statement if we throw some else's in there. It's just a big, long if-else statement with compound pieces. If root's null, else if the root's equal to the data, else if it's bigger than the data, else if it's less than the data. And it's way harder to read. But it's kind of cool that you can do a search of a binary search tree in one statement. But again, it only works, right? All of this only works if we really believe that these things work. And if you wanted to prove that this whole thing works, you do it inductively. You show that, you assume that these things work, and from that, it's easy to prove that this works. Because if you believe these work, then this is just how we search a binary search tree. And the base case, again, is when root is null, search clearly works because it returns not found. All right, well, to insert, we could search, and when we get down to the point where we found a null, we could back up one step and add our new node onto that child. We need to know what the previous node was, and we need to know whether our last movement was either to the right or to the left, so that we can put our new node, say 64, on the proper side. But again, let's think more recursively. So you have this big tree, and you want to insert into it. Do we know which half of the tree we want to insert in? If we're on the right, if we're bigger than the root, we want to insert into the right. If we're smaller than the root, we want to insert into the left. So a first order version of this might look like this. And we're assuming the number is not in the tree. Okay. So if number is bigger than root data, insert our number into the right subtree. Otherwise, insert our number into the left subtree. Now that's not going to actually work, but it's the right direction, right? We want to insert into one of our two subtrees, depending on how our number compares to the root. But we got to do a little more work than this. So think about edge cases. What happens if root is null? Well, we're going to segfault right away when we try to do root arrow data. So what should insert do if we pass it an empty tree and we say insert a 10 into this empty tree? What should happen? Build a new node and have that be the new root. So we need to change the root of the tree if the tree is originally empty. And this was the reason for which we introduced sentinel nodes in linked lists, because we never wanted to actually change that first node. We always wanted it to be non-null. We're giving that up in trees. We don't have a sentinel, so for an empty tree, the root is null. For a non-empty tree, the root is the address of the root. So we need an edge case here, which is if root equals null. So create a new node. Set it up, right? Set its data value equal to num, set its left and right children to be null. But in our main program, we're doing something like insert root, comma 10. Remember, that's not going to be able to change the value of root, right? Root is an address, but it's passed by value. So we really need to do something like root equals insert root, comma 10. And we need this insert to return a struct node star, which will be the possibly new root of the tree. Exactly. So if we start off with a null tree, we create a new node, we set it up, and we return the address of the new node. That's our base case. That gets us from a completely empty tree to a tree with one thing in it. But in the case of a non-empty tree, as we're moving down, so I'll go on the left now. Let's say we want to insert 15. So it's smaller than 50, so we'll insert 15 into here. And it's smaller than 20, so now we're saying insert a 15 into this tree. And 15 is bigger than 10, so we're saying insert a 15 into this tree, which is null. And that call to insert will return a node, which is a 15. But it's not attached to our tree yet. What we really need to do was take this right child of 10 that was pointing to null and have it point to our new node. So our insert statement becomes a little more complex. If our number is bigger than the root data, then we want to say root arrow right is equal to the tree that you get after you insert number into the right subtree. And this is only important in the case where you're inserting into an empty tree. And over here, we'd say root arrow left equals insert root arrow left number. And that'll give us a perfectly good insert routine. So that's even weirder to think about. So search is probably the easiest to think about recursively. Traversal is the next easiest to think about if you don't think about it too deeply. But this is an area where, in some sense, thinking about something too deeply actually does a disservice to you. And I'm not saying take this on faith, but when you're trying to figure out what it does, sometimes it's helpful to look at it from, 100 feet up and just say, yeah, it traverses the left, prints the node, traverses the right, makes sense. Sometimes you want to go down, you want to actually think about what's happening in these calls, and you want to keep track of them, and we'll do that tomorrow. But it's a dance, right? Sometimes you gotta sort of relax your mind and just sort of say, well, yeah, obviously this is going to insert on the right, and then tack it onto the right child, right? And that lets you move forward. But we still want to be able to actually understand what's going on here. But that comes with time. The more you do this, the easier it is to think about that part. So my suggestion is don't get too frustrated if this looks horribly confusing, right? Try looking at it from kind of a few steps back and just take on faith that this is going to insert my number into the right subtree. And if you believe that absolutely, convince yourself that this is the right thing to do. And that's a little easier sometimes. But we will take a look and see exactly what's going on here when we do this recursively. And recursion is a approach to programming we're going to use throughout the rest of this course and heavily in 223, and you'll use in most other things that you encounter in computer science. It's a really powerful way to think about things. 215, we look at this, we can solve towers of Hanoi recursively. We can generate Fibonacci numbers or factorials recursively, right? We can misuse recursion also. We can traverse a linked list recursively, print the node after the sentinel, and then traverse the list pointed to by that node. And we don't have to have a pointer that moves down the list, but we don't need to do that, right? It's not necessarily easier to do it recursively. But we can wield this hammer at a lot of different things. Okay, but we're absolutely going to want to use it for doing trees and some of the other structures we encounter here, and a lot of what we do in 223. So we'll be dabbling in this extensively, and it will get more comfortable over time. But think about this, kick it over, and tomorrow we'll go through some detailed tracings of some of these recursive algorithms, and then we'll talk about deletion, and then we'll talk about abstract trees.
So, are you saying it could use a while loop?
No.